Welcome to Op-Amp Stability Basics, Part 1. In Part 1, we will introduce some basic tools and concepts for solving any op-amp stability problem. After completing this course, the learner will be able to identify pole and zero magnitude and phase characteristics on a Bode plot, recognize intuitive models for an inductor and a capacitor, understand the op-amp intuitive model for inverting and non-inverting op-amp configurations, use the control system model to identify beta and 1 over beta from the op-amp external feedback elements, know the stability criteria for loop gain plots, gain proficiency in using the rate of closure stability criteria per 1 over beta plotted on AOL, and recognize that 1 over beta is not always the closed loop gain of an op-amp circuit. Let's first review poles and their key characteristics on a Bode plot. Recall that at the frequency of the pole Fp, the magnitude will be minus 3 dB down from the lower frequency gain. The magnitude slope after Fp will be minus 20 dB per decade. The phase shift at Fp will be minus 45 degrees per decade. The slope of the phase through Fp will be minus 45 degrees per decade, and flatten to 0 degrees 1 decade to the left of Fp, and flatten to minus 90 degrees 1 decade to the right of Fp. Note how the phase of Fp affects frequencies 1 decade to the left and right of its pole location. Now let's review zeros and their key characteristics on a Bode plot. Recall that at the frequency of the zero Fc, the magnitude will be plus 3 dB up from the lower frequency gain. The magnitude slope after Fc will be plus 20 dB per decade. The phase shift at Fc will be plus 45 degrees per decade. The slope of the phase through Fc will be plus 45 degrees per decade, and flatten to 0 degrees 1 decade to the left of Fc, and flatten to plus 90 degrees 1 decade to the right of Fc. Note how the phase of Fc affects frequencies 1 decade to the left and right of its zero location. For quick first-order assessment of our circuits under analysis for stability, it is handy to use intuitive models for inductors and capacitors. A capacitor will look like an open at DC and like a short at high frequency. In between DC and high frequency, the capacitor will look like a frequency-controlled impedance. Conversely, an inductor will look like a short at DC and like an open at high frequency. In between DC and high frequency, the inductor will look like a frequency-controlled impedance. For stability analysis, we will use this op-amp intuitive model. The op-amp will be modeled as a high input impedance, differential input to single-ended output, that is then passed through an AOL, the open loop gain function, and then through ZO, the small signal, AC, open loop output impedance. This is a non-inverting op-amp configuration and its control loop equivalent diagram. We will define a term, beta, which is the portion of Vout that is fed back into the inverting input of the op-amp, here denoted as VFB. Our control system equivalent diagram is used after some algebraic manipulation to yield the closed loop equation, Vout over Vin equals ACL or closed loop gain, which equals AOL over 1 plus AOL beta. For large values of AOL, ACL is approximately equal to 1 over beta. There are key factors in this equation we will use for stability analysis. AOL equals open loop gain, beta equals feedback factor, and AOL beta equals loop gain. Now let's look at the inverting op-amp configuration and its control loop equivalent diagram. We will define a term, beta, which is the portion of Vout that is fed back into the inverting input of the op-amp, here denoted as VFB. We will further define a term, alpha, which is the portion of Vin that is fed into the inverting input of the op-amp, here denoted as VFB. Our control system equivalent diagram is used, after some algebraic manipulation, to yield the closed loop equation, Vout over Vin equals ACL or closed loop gain, which equals minus alpha times AOL divided by 1 plus AOL beta. For large values of AOL, ACL is approximately equal to minus alpha over beta. There are key factors in this equation we will use for stability analysis. AOL equals open loop gain, beta equals feedback factor, alpha equals feed-forward factor, and AOL beta equals loop gain. Here are some key facts about beta and 1 over beta. Beta is easy to compute as it's the feedback network around the op-amp. Beta and 1 over beta are reciprocals of each other. There are easy rules and tricks to plot 1 over beta on open loop gain, AOL. Plotting 1 over beta and AOL provide a first-order stability check. It is easy to see how to modify 1 over beta to correct or move the intersection with AOL to ensure circuit stability. Notice the common denominator factor AOL beta in both the inverting and non-inverting closed-loop gain equations. So if there is a stability criteria for non-inverting, it will be the same for the inverting configuration. Now what if AOL beta equals -1? Then the denominator for closed-loop gain will become 0. The closed-loop gain now becomes AOL divided by 0, or theoretically infinity. If closed-loop gain is infinity, this implies any small change at the input will result in large changes at the output that will feed back to the input and result in even larger changes in Vout. This will result in oscillations and instability. When the op-amp circuit is used in the real world, think of each pin of the op-amp, plus in, minus in, VCC, VE, and output, as an input. A noise disturbance or switching power supply glitch on any pin can cause a marginally stable or unstable op-amp circuit to oscillate, overshoot, ring, and have a long settling time. Remember that we also refer to AOL beta as loop gain. Recall also that we have infinite closed loop gain when AOL beta equals -1. AOL beta equals -1 occurs when AOL beta's magnitude is 1, or 0 dB, and AOL beta's phase shift equals plus or minus 180 degrees. We will define FCL as the frequency where AOL beta equals 0 dB. Our stability criteria is that at FCL, where AOL beta equals 0 dB, its phase shift is less than plus or minus 180 degrees. The distance we are away from plus or minus 180 degrees phase shift at FCL is called phase margin. For a good stable circuit, we want phase margin at FCL to be greater than or equal to 45 degrees. To obtain AOL beta information, we must open the op-amp closed-loop gain model and inject a test AC signal, V-test, into the inverting input. In this loop gain test, the op-amp is open loop, and we can measure the key parameters of interest for stability analysis. Loop gain equals VFB, AOL equals Vout, and 1 over beta equals Vout over VFB. Now for SPICE simulations, we need to obtain our key stability terms. We want an open-loop AC analysis test to measure these parameters. Any AC SPICE analysis does a behind-the-scenes DC operating point analysis first to obtain linear, small signal models for all nonlinear components. We should always do a DC operating point analysis first and make sure our op-amp is in the linear operating region on its input and output. We will break the closed-loop op-amp circuit at the inverting input by putting in a large value inductor, LT. Remember, LT is considered to be a short at TC and an open at any frequency of interest. We will then inject a test signal, V-test, through a large value capacitor, CT, into the op-amp's inverting input. Remember, CT is considered to be an open at DC and a short at any frequency of interest. Since this technique will isolate the internal common mode and differential mode input capacitances of the op-amp, they should be added externally, as shown for accurate sims. If you were to use this technique and forget where to inject the signal, always inject it into the highest impedance node on either side of the inductor break, which will be the op-amp's inverting input. From this slide, we see the equations for our key stability analysis terms, AOL, 1 over beta, and loop gain, AOL times beta. Note the recommended dot option setting for LT SPICE for best stability analysis, to eliminate any DC current through CT, which would give an erroneous DC operating point. There is key stability information that can be visibly obtained from plotting 1 over beta on the AOL curve, as shown here. From the linear versus dB log math derivation, we see that on an AOL and 1 over beta plot that the difference between AOL and 1 over beta is AOL times beta, or loop gain. Note on the AOL and 1 over beta plot how loop gain changes with frequency. At FCL, the intersection of AOL and 1 over beta, loop gain goes to 0 dB. FCL will become a key point to apply first-order stability criteria. At FCL, the rate of closure of 1 over beta plotted on AOL will tell us, first order, if an op-amp circuit is stable or not. This is a first-order stability check and gives us no direct loop gain phase margin information. A SPICE loop gain test is needed to get accurate loop gain phase margin on a given op-amp circuit. It will also give us a powerful way to see how to compensate an op-amp circuit to make it stable. The stability criteria is that the rate of closure at FCL must be 20 dB per decade for stability. The rate of closure is defined as the absolute value of the difference in slopes between AOL and 1 over beta. In this diagram, we show several common cases of stable and unstable op-amp circuits using rate of closure. Once we are familiar with this criteria, it becomes an easy visual tool for stability analysis without having to do math on the slopes of AOL and 1 over beta at FCL. Let's take an example of an unstable circuit, as determined by rate of closure, and see how the AOL and 1 over beta plot correlate to a loop gain plot. Here at FCL, we see a 40 dB per decade rate of closure, which by this first-order criteria says we are unstable. There is information from the AOL and 1 over beta plot we can use to predict what a loop gain plot will look like. Since loop gain is AOL times beta, we predict a loop gain plot to have 100 dB minus 20 dB equals 80 dB low-frequency gain. Since poles in the AOL plot are poles in the AOL beta plot, we expect loop gain poles at FP1 and FP2. Since a loop gain plot is an AOL beta plot, and it uses beta, we expect it to have reciprocal poles and zeros from a 1 over beta plot. So in the loop gain plot, the 1 over beta, FC1, will become a beta pole. So by quick inspection, we expect a loop gain plot with 3 poles, FP1, FP2, and FC1. Here we see the equivalent loop gain plot from our prior AOL and 1 over beta plot. Remember, we predicted 3 poles at FP1, FP2, and FC1. Their associated combined phase plot is shown on the right. Loop gain is seen to be, as previously predicted, 0 dB at FCL, 10 kHz. Loop gain phase margin at FCL is seen to be 0 degrees. This is just a straightforward example to show how rate of closure predicted instability with 0 degree phase margin. Not all cases with 40 dB per decade rate of closure will result in 0 degree phase margin, but in general, all 40 dB per decade rate of closures will have low phase margin. 1 over beta is not always the closed loop gain of V out over V in. 1 over beta is the small signal, closed loop noise gain for the op-amp. Shown here is an inverting op-amp with an RC network across the op-amp inputs. The 1 over beta is as shown in our plot. Note how this RC network creates a 1 over beta that reduces loop gain and lowers FCL, compared to if just Ri were on the input and the V out over V in would be flat at 20 dB, out until 1 MHz. When loop gain goes to 1 or 0 dB at FCL, then V out over V in is forced to follow AOL down at higher frequencies.